Welcome to the second lecture of the transistor series. In previous lecture, we had an overview of transistor. There we have seen what are the different types of transistors, and now we'll be seeing the working principle of PNP transistor, how PNP transistor actually works. So let us have a look at the symbol of the transistor. So this is the symbol of PNP transistor and this is the symbol of NPN transistors. So now we are concentrating here in PNP transistor. So PNP transistor, if we have a look here, so let us call it figure number 1, and when no bias is applied, just like we have discussed in diode, PN junction diode. So here also we have PN junction, that is junction between emitter and base. So this is our emitter and this is base. So emitter base junction JE and collector base junction JC. So both are PN junction. So as usual we shall be having some barrier potential, and you see here the uh, N side. So this is your N, base is N material, P is emitter and P is collector. So due to the diffusion of the majority charge carriers, so here we will be having the electrons, more number of electrons, and here we will be having more number of holes naturally, that is due to the barrier potential. Similarly here also we will be having the same thing, and as a result of that barrier potential, positive and negative polarity will be like this. Now if we consider that we are making the base emitter junction forward bias and collector base junction as reverse bias. So here this particular configuration is called the common base configuration, because base is common to both input side as well as to the output side. However, this will be discussing different configuration of transistor that will be discussing in the subsequent lectures. So currently we are not saying what is the configuration. For the time being we are trying to understand that we are having at the input side collector emitter based junction as forward bias and collector based junction as reverse bias. Now if you see that here the majority charge carriers are holes, mainly holes are here. So if we apply positive potential here, so they will be forced to penetrate in N region further beyond the barrier potential. And here collector is like an wicket keeper. In cricket match we have seen that wicket keeper is collecting the balls. So here also the collector is collecting what? It is collecting the majority charge carriers coming from the emitter region. Now question arises here, we shall not have the sufficient recombination. No, we shall not have, because it is, first thing is that the base region is lightly doped. This is lightly doped and it is very thin compared to emitter or collector region. So thin, as well as it is having less number of majority charge carriers. That means here we have the electrons, so less number of electrons, so recombination will be less. However, due to the small recombination, we'll be having a small current, what we name as base current, and here the holes will be penetrating up to the collector. So collector will be collecting here, but this current, whatever we'll be having, that will be little less compared to the emitter current. Whatever emitter current we have here, will be having it little less, because some part will be going out from here. So if we have a look here from the symbol point of view, here we have used the symbol of PNP transistor that we have seen in the slide 1 as well. So here, due to the recombination, so 98% more or less 98% of the holes will be allowed to pass to the collector, and as a result of that, what we can say that IE is equal to IB plus IC. So let us call it equation number 1, or in other words you can write IC, that is the collector current, which is nothing but IE minus IB. So this the relation of the currents, and the direction of currents are very important here. So current, flow of current here mainly because of the holes. So the direction of flow of holes and direction of flow of current, that will be same. Now if we vary this voltage here, then the uh, uh, value or magnitude of IB, IC and IE will also change. But large part of the emitter current, IE, flowing into the transistor, that constitutes the current in the collector region, IC. However, there are some, since it is in reverse bias, so we shall have some reverse saturation current. Somewhere it is called dark current, and we are naming it as ICBO. So because of ICBO, whatever IC we are saying here, it will be slightly higher than that, and actually IC will be given as alpha DC into IE plus ICBO. So call it equation number 3. So in this relation, we are finding another term called alpha DC. So what is this alpha DC? Alpha DC, mathematically it is given as IC minus ICBO divided by IE. But what is the significance of it? Alpha DC is basically the part of IE, that is your emitter current, which flows from emitter to collector. So part of IE, we have seen here, the entire IE is not coming here. A part of it, but which is very close to it. So that part we are calling as alpha DC, and alpha DC is ranging from 0.96 to 0.99 depending on what kind of recombination is taking place. As I have mentioned, it is around on an average 98%. So 96 to 99% you can see will be getting collector current as the part of emitter current. Now ICBO, it is very less in practice. So if we consider IC much greater than ICBO, then we can approximate IDC as IC divided by IE. So this is one interesting relation. Alpha DC is equal to IC divided by IE. So what we can say, IC is the output current and IE is the input current. So this is basically, this relation is basically saying us a current gain. However, this current gain typical value we have already seen, it won't cross 1. So it is 0.96 to 0.99. So that means though we are calling the term, using the term gain, but there is no gain in practice. And this is here we are using the common base configuration. So we further rename it as common common base current gain. So under common base configuration, we are having the current gain, which we are calling as common base current gain, and which is denoted as alpha DC. So that's it about the working principle of PNP transistor. Next lecture will be considering the working principle of NPN transistor, where holes will be the majority charge carriers, and it will be interesting to see the uh, flow of current direction, especially the direction of flow of current. So that will be quite interesting. So here we end this lecture. Thank you very much for listening.